All right, good morning, everyone. Hope you guys all had a nice break. Okay, let me just show the bell schedule. Hope you guys can all see my screen here. Okay, so because there's only 5 minutes, or each of the classes are only 50 minutes long, and there's only a 5-minute break between classes, so everything's kind of moved up, meaning that this week, at least just for this week, we'll be done with 7th period by 2:40, and then the last part of the day, 2:45, 3:30, is just help session or virtual office sessions or virtual office hours. All right. Let's see. Hopefully you guys all had a chance to print out the notes. If not, you kind of just follow along, but it's just helpful to have the notes printed out. That way you can kind of follow along as I'm going through each of the problems. But assuming that we're back in person in the classroom next week, I will have the packet and the calendar for you. But in the meantime, maybe you can just kind of print out page by page for each of the days that we're doing notes for this week. Right. I'll also print out a calendar, and all this is on that link that I just put on in the chat box. Okay. So we're going to start chapter 4 today. So first semester was all about derivatives, which is slope related. This semester is all about antiderivatives, which is basically undoing the derivative process that we learned first semester. So application-wise, what that means is now we're going to be dealing with area. Okay, so what that's going to translate to is we're going to be able to deal with area, volume of regions under a curve. So first semester was all about finding the slope of an ever-changing curve. Now we're dealing with area under an ever-changing curve. Okay, so we're going to be starting off with approximation of area under a curve, but really today is just kind of learning about some of the underlying tools that we need to help us to find those approximations Wednesday and Thursday. So today we're just going to be learning about sigma notation, kind of getting practice with those summation rules. And then tomorrow we'll move on to approximation using rectangles. And then eventually we're going to get to a much more efficient way of finding area under the curve using power rule for integrals, which is just basically power rule for derivatives, but then we're kind of changing those operations around so that we're kind of undoing that derivative process. We'll finish up notes for 4.1 on Monday, and then just because we're virtual for all these days, I think it's maybe good to kind of have additional days for quiz review. So we'll start quiz review Tuesday. We'll have 3 days for quiz review to kind of get us back into the swing of things in the classroom, and then we're having a quiz next Friday. Okay, we're gonna have homework assigned for each of the days, but I probably won't check homework until I'll probably check it all next Wednesday. Okay, but it's good if you guys can kind of keep up with each of the homework assignments. Okay, so that you're not having to do it all at once. Okay, any questions about the calendar? All right, so let's start notes for 4.2. Hold on a second. Okay. All right. So sigma notation. You've seen this before, but we're going to just review this. So sigma notation. This is just a notation that represents the fact that we want to add a bunch of terms together. Okay, so that's all this means. Shorthand form of representing the fact that we want to add a bunch of terms together. Okay, so let me kind of review each of the parts that we see in front of us. That I is our variable index, or index variable. The 2 represents the lower bound. This is the first value that we want to enter into the expression. Okay, and then this value is the upper bound. Okay, this is just an example. It's not always going to be 2 and 5. Just want to kind of show you what the result of this would be. Now, a sub I would represent our argument expression. So you can also think of this as your formula rule. Think of this as your rule of sequence. Okay, so let's say this is an example from 2 to 5. Okay, so this is what would result from this particular expression. So what we do here is this tells us that the first value we're going to plug in is 2. We'll plug 2 into the expression, and that will be represented as a sub 2. Okay. We know the summation indicates that we're going to be adding a bunch of terms together, so we'll do a plus. And then we're always going to increase our lower bound by 1. So the next value that we plug in is going to be 3. So we plug 3 in for I, so that will give us a sub 3. Keep going. 4, we get a sub 4. Keep going. 5, we get a sub 5. And that's where we stop because 5 is the upper bound. So that 5 tells us that this is the last value that we're going to plug in for I before we stop. Okay, so you can see here, there's only 4 terms. Okay, I want to kind of, one of the misconceptions is that students think that this 5 means that there are 5 terms. Okay, not necessarily, because we're starting at 2. So 5 doesn't represent that there are 5 terms. 5 means it's the last value for the variable I. Okay. Let's see if we can practice adding terms together. For example, 1. So we can see that our lower bound is 2, our upper bound is 4. We're adding a bunch of terms into this expression I squared plus 1. So start with lower bound, plug 2 in for I. Okay, so that represents the first term. Next up, we're going to increment 2 by 1, so we're going to go up to 3. We plug 3 in for I. Plug 4 in for I. And that's where we stop because 4 is the upper bound. Again, the 4 doesn't mean that there are 4 terms. 4 means that that is the last I value that gets inserted into I. Okay, so now we're just going to be adding these terms together here. 4 plus 1 is 5. 9 plus 1 is 10. 16 plus 1 is 17. So we get 32. Okay, any questions here? Now, this is not terrible to do if there's only a few terms, right? But imagine if we're going from 1 to 50 or 1 to 200 or 1 to 1,000. We really don't want to spend the time to do everything manually if there are a lot of terms. So we have these summation formulas that can handle certain situations where there are a lot of terms. These formulas will allow to kind of give us a shortcut as long as it fits under one of these formulas or these rules. Okay, so let me kind of go through what each of these rules mean and how to interpret it and in what situations we want to use it. So an example of one, let me do an example of this first rule here. This is saying that I want to go from 1 to n, but my rule is just 1. Okay, when I do that, my sum is just going to be the same as the upper bound. Okay, so here's an example. Let's say I want to go from I equals 1 to 5, and then my summation rule is, my argument is 1. So what we're going to do is we're going to just, let's do this by hand and kind of show that it will match with what we see in this rule, which is the same as the upper bound. So what we do is we start off with lower bound, we insert 1 into the expression. There's no variable here, so this will stay as 1 plus, we plug 2 in for I. There again, there's no I, so all we're left with is 1. Plug 3 into the expression. Again, there's no variable. We're just left with 1. Plug 4 in. Plug 5 in. 5 is the last value for I. Again, there's no I variable, so we're just left with 1. If we add all these ones together, we get 5. And 5 is the same as the upper bound. All right, so if my summation sequence rule is just 1, then my sum will be the same as the upper bound. I'm just adding a bunch of ones together. Right. I want to show how a rule looks if it was summation I. Let's say I have summation sum from 1 to 5 for I. Okay, again, I'm just, we're going to do this by hand first, and then I want to show you that this rule actually will match if we were to just do with what we found by hand. Okay, so if I have summation of 1 to 5, my rule of sequence is I, then I'm going to start with 1, right? Plug 1 in for I, I'll get 1. Plug 2 in for I get 2, 3, 4. I stop at 5 because here 5 is given to us as the upper bound. So 1 plus 2 is 3, 3 plus 3 is 6, plus 4 is 10, plus 5 is 15. So we know the sum is 15. Now let's see if it will match with the rule that we have here. Okay. It should match. Okay, so if I enter 5 in for n, right, that's my upper bound. Right, my upper bound is my n. So if I insert 5 in for n, I get 5 times 5 plus 1 all over 2. So 5 times 6 is 30. 30 over 2 is 15. We see that the rule matches with what we know to be true if we were to work it out by hand. So it's not bad if we only had a few terms, but imagine if we're going from 1 to 100 or 1 to 200, we'd much rather use the rule than having to add all the numbers together manually. Okay. Same thing, we have a rule for I squared. This would be true if it was like 1 squared plus 2 squared plus 3 squared all the way to whatever that upper bound is. Much faster to use this rule if it's a big n value. And also a rule for I cubed. You take the upper bound, insert it in for the n's. N squared times n plus 1 squared all over 4. And this fifth rule is really just showing us that if we have any coefficient that is really not part of the rule, we can push it out in front so it's not distracting us, so that we can kind of take care of the parts that is impacted by the rule, resolve that first, and then we can multiply that c at the end, or that coefficient. That could be a number like 6 or 5 or 8. We can kind of push it out in the front so that we can have an easier time kind of seeing the rule that we want to be applying. Okay, so examples 2, 3, and 4, we're really just going to be practicing these summation rules. We don't want to be adding them by hand. We really want to take advantage of these summation formulas. Okay, so here's example 2. Now, what you can see here is that this looks a lot more complicated than these individual rules. So what we're going to do is we're going to kind of separate into individual parts. As long as we have a plus or minus between these terms, we can think of these as separate summation rules. Okay, so okay, so I'm just separating them, assigning that summation notation for each of the terms. And I'm also going to spend the time to push any coefficient out in front. So I'm going to push the 3 out in front. I'm also going to push the 2 out in front too, so that we can have an easier time matching the rules that are going to be applicable for us. Okay, so the 3 is going to get pushed out in front here. I'm also going to push the 2 out in front. If I push the 2 out in front, what's left is a 1, because 2 times 1 is 2. It helps us because if we push that 2 out in front, we can kind of see that summation 1 is the one in play for this one. Okay, any questions so far? All right, so I'm going to box off the parts where the rules are going to apply above. Okay. And the 3 and 2 will just get multiplied with the result that we find in each of these sums. So we know that the summation 1 to 8 for I squared is going to match this rule here, n times n plus 1 times 2n plus 1 over 6. The n is going to be the upper bound, so we're going to replace each of the n's with 8, right? So the upper bound n is going to get inserted to each of the n's. Upper bound is going to get inserted to each of the variables there. Okay. So the rule says n, which is 8, times 8 plus 1 times 2n plus 1. So that's 2 times 16, or 2 times 8 plus 1. All over 6. Plus 2 times summation from 1 to 8 for 1 is just going to be 8, right? That upper bound is just going to be, because I'm adding a bunch of 1s together, it's just going to be the same as my upper bound, so it'll be 2 times 8. Okay, so now it's just a bunch of numbers that we can multiply and add together using our calculator. Any questions so far? Does everybody see how we're using the rules to kind of help us get this down to a number? Okay, so 8 times 9 times 17 all over 6 times 3. In the calculator, that will give us 612 plus 16. Okay, any questions so far? Okay, let's look at example 3. Same idea. We're going to be involving the rules that we see above, but right now what's causing an issue is that we have, it's not quite I squared, it's I plus 2 squared. So we really want to spend the time to expand this out. We don't want any parentheses kind of getting in the way of allowing us to match the rules. So we're going to spend the time to expand. Make sure, though, that we don't just distribute the 2 through. This I plus 2 squared, we really want to spend the time to think of it as I plus 2 times I plus 2. All right, we're going to FOIL this out in the correct way. Okay, any questions so far? Right, we're FOILing this out, combining like terms, and now, just like before, we're going to split up into individual parts, push out any coefficients so that we can match exactly the rules that we want to use. All right, are we okay going from here to here? All right, we have 3 separate terms. Each term is going to get its own summation. And then along the way, I'm also going to push out any coefficients so that I can get a clean look for the rules that I want to apply. I don't want any of these numbers to kind of get in the way of me matching the rules that I want to use. So I got a clean match with this expression, a clean match here, and a clean match here. Okay, so for summation I squared, I'm going to use my first rule. My upper bound is 10, so I'm going to insert 10 in for all the n's. Okay, so 10 times 10 plus 1, which is 11. 2 times 10, 20 plus 1 is 21, all over 6. Okay, summation from 1 to 10 for I. So 10 times 11 all over 2. Summation 1 is just going to be n. My upper bound is just going to be 10. And now it's just a matter of using our calculator to add those numbers together. Here we get 10 times 11 times 21 over 6. Again, the calculator gives us 385. Okay, 2 times 110, 220, plus 40. Okay, any questions so far? Okay, 1 second, guys. Okay, now we're moving on to something that's a little bit feels a little bit more abstract. Okay, because unlike examples 2 and 3, we don't have a numeric value for our upper bound, which means that our answer will stay kind of abstract in terms of n. Okay, we're still going to go through the same process. It just feels a little bit different because instead of I, now our variable is k. Now, what to do with the n? Okay, so what I want us to be able to understand is that the n is kind of as a constant. So treat n like you would if it was a 10 or an 8 or a 5. Okay, and what that means for us is if we see a 1 over n, we're just going to treat how we would before if it was a 3 or 2 or 5. Right? It's just going to be stuck in front of the rule. Okay, it's not going to impact the rule. It's only the k that we want to isolate. The n is really just a coefficient. Okay, so treat n treat n as a constant. Right, so just like before, we're going to try to clean up the parentheses. So I'll distribute the 1 over n through. Now that I have each of the terms separated or the 1 over n distributed, I can treat this like two separate summations. And along the way, we're treating n as a constant, so I'm pushing the n out in front as well. Okay, any questions so far? To get from here to here to here, are we okay? Now the summation k squared is going to be the same as summation I squared. Okay, instead of using I, now it's a different variable, but it's still the same rule. So we can box this off. We know we have a substitution for this piece. And then summation 1, we have a rule application for that first rule as well. Right, so the k squared, we can use this third rule. Right, so n times n plus 1 times 2n plus 1 over 6. We don't have a substitution for n, so we're just going to use n's like how we see here, right? We don't have a numeric value to plug in for n, so it'll stay as n. And summation 1 is just n. Okay, let's do some cleanup here. All we're doing is just kind of combining terms that we can or clean up as we can. The n's can cancel out here within this fraction. Within this fraction, the n's can cancel out. So we're left with n plus 1 times 2n plus 1, which is 2n squared plus 2n plus n plus 1 all over 6 minus 1. Okay, combine some like terms. I'm also going to see if I can separate each of the fractions. So various ways that you can clean this up. So I can think of this as 2n squared over 6. 2n plus n is 3n over 6. Plus 1 over 6. And I can think of 1 as a 6 over 6, just so that I can work towards combining some like terms with that 6 of the 6 in the denominator. So here I can reduce each of the fractions here, n squared over 3 plus n over 2. And then 1/6 minus 6 over 6 is 5/6. Right. Because we don't have a numeric value to start off, the best we can do is leave our sum in terms of n for this problem. Okay, so we're going to become we're going to continue to use the rules on the second page of our notes, but we're going to be it's going to become more abstract. We're going to begin to push this n out to infinity. Okay, out to infinity. And this is going to be a useful tool that we'll be using tomorrow and the next day and the following day. So let's go to the back page. Any questions here? Are we okay? See if there's any questions. All right, so second page. All right, limits as n approaches infinity. Okay, let's review what we did. So think back about finding finding horizontal asymptotes. So as a review, here's an example. If we're going out to infinity, the way we find limits, we don't plug numbers in, right? All we do is we just compare degrees. And if the degrees match, then all we do is we find the ratio of the leading coefficients. So we identify the highest degree. The highest degree for numerator is 2. The highest degree from the denominator is also 2. We basically can ignore all the other terms that don't have that high degree. It's not going to play a role to find the limit. These two terms are really dictating what this value is headed towards. So because the degrees match, we just take the ratio of the coefficients. So the coefficient in front of this n squared is 3. The coefficient in front of this n squared is 5. So our limit is just going to be 3/5. So what this tells us is basically that if we keep increasing n out to infinity, 100, 200, a million, a billion, this fraction will just get closer and closer towards the value of 3/5. Okay, and that's what this is saying. So let's practice that with example 5. Okay, so let's say we have a rule of sequence that's shown as 1 over n squared times n plus 1 over 2. Find the limit of this expression as n approaches infinity. Okay. All right, so first thing I'm going to do is just try to clean this up, right? I want to kind of get all this cleaned up and combined together so I can see what the true ratio or what the degrees are between the numerator and denominator. Because right now things look separated. Okay, I'll distribute the n through. The 1 is not going to factor for us here. So distribute the n through, I get n squared plus n. Denominator, I can just make this 2n squared. Okay. We're approaching infinity, so we can just look at the degrees between numerator and denominator. They both have a degree of 2, so we know that we can just take the ratio of the coefficients. There's a hidden number in front of this n squared, which is 1. There's a 2 in the denominator, so my limit is just going to be 1/2. Okay. So moving on to example 6, same idea. We're still going to infinity here, but now we're going to have to maybe involve the summation rules from the previous page. Okay, so let's do this step by step here. Let's distribute, get some of the parentheses out of the way. Okay, multiply the numerators together, multiply the denominators together. Okay, 4i over n squared. Okay, what we want to do is we want to kind of strip away all the parts that's not part of the rule out in front. So the 4, and remember we talked about on the previous page, if we see any n's, we're going to treat it like a constant. So that's not part of the rule that we want to match with the first page. Right, we want it to look like one of these, right? Either summation 1, summation I squared, summation I cubed. We want to push anything that's not part of the rule out in front. So the 4 and the n squared can be pushed out. Okay, so now we can cleanly see that the rule that we want to apply is that summation 1 to n for I. So let's put that formula there. Summation I is just going to be n times n plus 1 over 2. Okay. Made a substitution there. So now it just feels like the previous problem, right? We're just going to get all this cleaned up so that we can cleanly match the degrees between numerator and denominator, and then take the ratio if the degrees match. So I'm distributing the 4n through the n plus 1, so I get 4n squared plus 4n all over 2n squared. Right, so we see the degrees, they do match. So we simply take the ratio of the coefficients. The 4n is not going to play a role, only the terms for the n squared. Okay, so 4 over 2 is just going to be 2. That's our limit. All right, so we're going to end with example 7. More complicated because there's more cleanup that needs to happen. So we'll do this piece by piece here. All right, so I'm going to make sure that we take the time to FOIL, right? I know it's tempting to just take that 2 and distribute it through, but we can't do that if there's a plus in between. So we really want to spend the time to distribute that through. So we want to think of this as 1 plus 2i over n times 1 plus 2i over n, right? All right, let's FOIL this out. Combine like terms. And then I'm going to distribute this 2 over n through. Okay, so I'm just doing piece by piece, right? I fold out the parts that I want to clean up, and then I want to distribute that 2 over n through. That way I can get every term nicely separated with no parentheses in the way, and then I can kind of begin to identify each of the summation rules that I want to apply. Sorry, 2n cubed here. Oh, my bad. 8i, there's not the 2 there, it's just n cubed. right? 2 over n plus 8i over n squared plus 8i squared over n cubed. Okay, right? So let's assign that summation to each of the terms. Now that we have everything separated. All right, so I'm going to assign the summation to each of the terms, and along the way, I'm also going to push out any distractions that's not part of the rule. So here, there's no I, right? So I can push everything out in front, but what's left over is a summation 1. Okay, everybody okay so far? All right, there's no I, then there'll be 1. Here, there'll be summation I. This one will be summation I squared, and we pushed out all the coefficients. That's not part of the rule. And then we're just going to find the parts that need replacements. Okay, it's going to feel a little messy with all these terms here, but a lot of this will go away because each of the fractions, we can just find the ratio of the coefficients. Okay. All right, so limit as n approaches infinity, 2n over n, 8n squared plus 8n. This is 2n squared. Okay, so each of these fractions, all we're going to do is we're just going to identify the highest ratio of the coefficients, right? So here, this is 1 and 1, so that's just going to give us 2. Second fraction, we see the ratio of the coefficients is going to be 8 and 2 because the degrees here, the highest degree within this fraction is 2, so we just take 8 over 2. And the third fraction, we just have matching 3s. We don't care about anything that's lower, so just 16 over 3. So we get 2 plus 4 plus 16 thirds, which will just give us 26 over 3. Okay, any questions here?
Where did 16 over from? Would it be 6?
Okay, how did I get this 16, you mean?
Well, how'd you get the 3 from instead of 6.
Oh, my bad. I reduced it before I got to the end here. So my bad. Okay, sorry. It should be 16/6, and it reduced to be 8/3. And 2 plus 4 plus 8/3 will give us 26/3. Yeah, miscopied my notes. Okay, I do want to point out something here. I know these aren't too hard to clean up, right? This feels a little messy, right? You got to FOIL all this out. So I have a bit of a shortcut, okay? The shortcut is that we really don't care about this 24 and the 8, right? It doesn't have to play any role for us. So the way that you can just skip all the other messiness and just get to what you need, just take the first part of every term and multiply that together. So the 8, the n, and the 2n, those are the only things that's making an impact for the numerator, because we're doing limit as n approaching infinity. So the highest degree and the most important information is only going to come from the first term. Every other term is just going to produce something lower. So 8 times 8 is 8n. 8n times 8, sorry, 8n times n is 8n squared. Plus 2n, sorry, times 2n is 16n cubed. So if you don't even include this, that I'll be fine with it. Okay, if you can just identify, okay, the most important part is that 16n cubed. I don't really even care about the rest of this, and just leave it like this and say plus dot dot dot, and just get that 16/6 to show up. Okay, that's a bit of a shortcut rather than having to FOIL each of the parts out. Does that make sense? Okay, I'll leave this up in a few minutes here, but I just want to kind of go over the fact that we have homework tonight from 4.2. If you go on the website, at the very top of the page, I have the links for the textbook pages, so you can click on 4.2, which will take you to page 263 and just do 1 through 19. I'm not going to check any homework this week, but next week when you guys are back, I'll check homework on Wednesday. But it'd be good if you just kind of keep up with the homework. That way you can show it all to me when I come around and check your homework on Wednesday. Okay, and the calendar is on my website as well. So everything is on that page for this unit. All right, any questions? All right, I'll hang around for a few minutes, but other than that, we can end class here, and hope you guys have a great day. See you tomorrow.
Thank you.
Thank you.
Thank you.
See you guys. Have a great day.
Thank you.
Thank you.